Hello, welcome to Bare Metal Machine. I'm Jeff Adia. Today I want to give a little demonstration that shows the accuracy and repeatability of the motorized Phase II Rotary Table. If you're not familiar with these tables from my other posts, here's two specimens right here. This is the Phase II 8-inch Rotary Table, horizontal version. Okay, and here's what it looks like before the retrofit. And here's the same table with a stepper motor retrofit to it, the coaxial drive stepper motor. And here's the controller. I'm just using a Raspberry Pi computer, and so it just has a little command mode interface, and the controller, of course, is down here. Right, that's where all the electronics are and the intelligence components that are necessary for driving the system. All right, so stand by and we'll get into this demo. In the documentation that comes along with these rotary tables, they give an inspection report that shows the accuracy of the rotary table and a number of different parameters. But the one we're mainly interested in is indexing accuracy. And on this little form it shows 80 arc seconds. I'm not really sure what they mean by that, but I suppose it means that any particular angle that you dial up on this table, you could be sure that you're within 80 arc seconds of the actual position. I might also interpret that as plus or minus 40 from the desired position. What are the practical, what's the practical interpretation of 80 arc seconds of indexing accuracy? Okay, so here's the setup I'm going to use to demonstrate the repeatability of the rotary table. You notice I've got this indicator set up, and the indicator tip is 5 inches from the center of rotation. Right, so here to here is 5 inches. And the reason it's 5 inches is because I consider the working envelope of this 8-inch table to actually be more like 10 inches. And so I want to have it out here at a 5-inch radius so that I'm always seeing the worst case angular error. And it's set up on this height gauge because I want to be able to move the indicator independent of the machine. I don't want to move the quill or any of the machine's axes and introduce any of their errors into this. Okay, so let me get a little closer and we can do the test. Okay, so look at the indicator now. We're at plus 2/10. This is a 10th indicator. And I know that might sound like overkill for what we're doing here, but I really want to split hairs here and be accurate about in this demonstration. Okay, so we're at plus 2. So I'm just going to move the table away 5 degrees, A minus 5, right, and then back again, back to 0. And we're at a little under plus 2. One more time. Okay, back again. All right. Now I'm going to go from the other direction. A plus 5. Back to 0. Okay. And we're at about plus 1. A minus 5. A 0. Okay, about plus 3 that time. Okay, so it looks like it's repeating within a couple of tenths. Now what we're also really demonstrating here is the backlash compensation in action. So I was moving at 5 degrees, and 5 degrees is 25,000 pulses. And so you can see anytime the rotary table changes directions, it has to apply the backlash compensation, which happens to be 135 pulses. And you can see here, when I programmed it to move that last angle back to 0, it had to change directions to get there. So it applied 135 more pulses. So what you're seeing here is the backlash compensation in action. If it wasn't set right, it wouldn't get back to 0, as close as it is anyways. And how I determine that 135 pulses is another story. I'll make a different video on that. But this is really a demonstration of the backlash compensation in action, and so I would call a couple of tenths of repeatability coming at it from either direction pretty good, and I'll take it. Okay, so here's the setup I'm going to use to demonstrate the accuracy of the table. I just have this indicator chucked up in a spindle, and that same parallel has now been moved to the interior of the table because we're not really concerned about the radius anymore. We just care about angular measurements. So in order to do this measurement, I have to have that parallel to the x-axis. And so that's going to be, you know, at an angle of 0 degrees. And I'm going to move it to some arbitrary angle and measure that angle. But I have to have a reference, and that reference is going to be that parallel to the x-axis. And my controller actually gives me a handy way of making that alignment a little easier. Okay, so to align the table with the x-axis, what we have to do is take 2 points. Right? This is actually kind of a common trick that a lot of machinists would know. You take 2 points, one here, and you just solve a little triangle to figure what the angle is that the parallel is at, and then you move the table that amount of degrees, and voila, you've canceled out that angle, and you're now parallel to the x-axis. Okay, so all I got to do is take a point here, right? Get touch the indicator off to 0. Okay, so here we just want to zero out our DRO, x0, y0, right? And now take another point, get the indicator away, take another point down here on the other end of the parallel. All right, good enough. So now go back to indicator 0. Right about there. Okay, so there's our displacement. Now I simply go over here to the controller and I type in, let's see, Command Z, and I give it minus 5.75649, and then minus 0.2283, and the table already moved. Okay, now let's see how close we are. I'm going to go back to indicator 0. Okay, close enough. That actually looks pretty good. It's within a couple of tenths of being parallel to x. Minus 2. Minus 1. It's within a couple of tenths, all right? So I'm going to call that good. That is now 0 degrees, and we can make our angular measurement relative to that parallel. Okay, so the setup we're going to need to demonstrate the accuracy of the table is going to involve a sine bar, right? And of course a gauge block. And that gauge block is actually set up to an arbitrary angle of 25.429 degrees, right? So, you know, with this kind of arrangement, with the sine bar and the gauge block, I can move the table to that angle, and then the sine bar is going to be parallel to the x-axis. And then all we need to do is indicate along that sine bar, and we'll get a reading of how close we are to that true angle. So let me get this set up proper, and then we'll take a look. All right, so I think we're ready to go. We got the sine bar and the gauge block all set up. All I need to do is move the table so that the sine bar is parallel to the x-axis. Okay, and so to do that, I come over here to the controller, and I give A minus 25.4295 degrees, and then go. Okay, table takes off. Okay, let me get the indicator set up again, and we'll have a look. All right, here we go. Now we got the indicator set up, and it's sitting at plus 0.2. Now we need to run the length of the sine bar. Minus 1. And back to about 0.2. That minus 1 dip is probably a little bit of a dip in the sine bar itself. It's not perfect. And we're back to about 0.2 there. So this looks awfully good. I'm going to call that good. About 0.2 of a thousandths over the length of that sine bar. Okay, now let's talk about what that means. But before we do that, just to be honest, let's make sure that the table can get back to 0 degrees and that the parallel is still parallel again. All right, that will prove that we actually went to some arbitrary angle and then back to 0 again. Okay, so let me command the table to go back to 0. 0. Go. Okay. All right, now let me get the indicator set up again and we'll tap. Okay, here we go. Indicator set up again. Parallel is aligned with the x-axis. Let's see how close we are. Okay, about minus 1/10. Actually, it looks pretty good. So, about plus 2/10. Yeah, a little over 2/10. So it's probably within 3/10. All right, so we got back to 0 within 3/10 of a thousandths parallel, and that's actually looking pretty good. All right, so the certificate of accuracy form that ships with these rotary tables, they're showing the indexing accuracy of 80 arc seconds. In the same breath, they're calling this a high precision rotary table. I don't know in what universe 80 arc seconds of indexing accuracy constitutes high precision. And here's why. Because, well, first of all, let's get 80 arc seconds into decimal degrees, which is 80 over 3600. Okay. And 80 divided by 3600, that's 0.022 degrees. So if you just make yourself a little mock triangle, right? You know, these are just approximations, by the way. 0.022, and this is 4 inches because that's the radius of the table. Well, then what is this leg? Well, it's the sine of this angle times 4, which is about 1.5 thousandths, 0.0015 inches. I don't know about you, but that's a country mile. That means that if you were indexing to some particular angle and going to machine some feature at that angle, then that feature right off the bat is going to be off by 1.5 thousandths. And so I think we've actually shown that we can actually do a lot better than that. For instance, you know, when we did the parallel measurement, when I was aligning with the parallel with the table, we only had about 0.3 of a thousandths of indicator deflection. And then when I put the sine bar on there, we had another couple of tenths. So even if it was, let's just add those together and say that it was 0.5, right, of TIR along that sine bar. I actually consider the working envelope of this table to be 5 inches in radius, because I believe that the working envelope, in practice, I've shown it to be 10 inches, not 8. You can actually go out another inch before you're stressing out any of the table's parameters. So anyways, if you had 5-inch radius, and let's say that just to be pessimistic about it, we had 0.0005 inches along the sine bar. And then what is this angle? Okay, well then it's going to be the arctangent of these two values, 0.0005 divided by, actually no, let's be even more honest about it. The sine bar is actually 5.75 inches long, okay? All right, and so let's say we had 0.5 TIR along that sine bar. Let me go 0.0005 divided by 5.75 is that, so that's the tangent of this angle, right? So if I take the arctangent of that, so let's say we had 0.5 TIR along that sine bar. Let me go 0.0005 divided by 5.75 is that, so that's the tangent of this angle, right? So if I take the arctangent of that, I get this number, and I multiply that times 3600, and I get 17.9. I get 18 arc seconds. Okay, that's a far cry from 80. And so I think that what we've demonstrated here is that, with the stepper motor, rigged for 20,000 pulses per revolution, and a little attention to detail regarding the backlash compensation, you can actually get indexing accuracy much better than 80 arc seconds. In fact, a machining feature being off by plus or minus 5/10 out at a radius of 5 inches from the center of rotation, that's pretty good. That's pretty darn good, especially for milling machine work. And so those are my conclusions, that the table is probably much more accurate than they give it credit for, and especially with the stepper motor on there, you can index to, you can actually index to, you can program it to 3 decimal places. But are you really getting that? This is actually probably a topic for another video, but you can program this thing to go to, like, as I showed earlier, 25.429 degrees. Well, are you really getting that kind of accuracy? Well, 0.001 degrees, that's 3.6 arc seconds. And no, we're not getting that kind of precision. But we're getting awfully close. We're getting within, probably plus or minus 20 arc seconds to be generous, and maybe even better in some cases. So you can program it to 3 decimal places, but you're not really probably getting there, because and why should you? I mean, this is a feed-forward system. It's not a feedback system. There's no encoder feedback or anything like that. So for a feed-forward system with just a stepper motor, I think we're doing pretty good, and we're doing, I believe, a lot better than what the manufacturer states. All right, so that's my conclusion on the Phase II Rotary Table. And any questions, just leave them in the comments, and I'd be happy to answer any questions. Thank you.